Right now, as you sit here, every atom in your body is made of matter. Protons, neutrons, electrons, ordinary stuff. But for every one of these particles, nature has a mirror twin, an identical copy in almost every way, except flipped, reversed. And if these two versions ever touch, even for an instant, both vanish completely, not into dust, not into smaller pieces, into pure energy. A flash of light and nothing left behind. The early universe made equal amounts of both matter and its mirror. By every known law of physics, they should have destroyed each other entirely. The universe should be empty. Just light. No atoms, no stars, no you. And yet, here you are. Something happened. Something very small. And tonight, we're going to find out what. If you find this kind of deep exploration fascinating, a quick like or subscribe really goes a long way in helping the channel grow. It takes a moment, but it makes a real difference for me. Now, let's begin. Let's start with something fundamental. You are made of particles. Everything around you is made of particles. The chair you're sitting in, the air you're breathing, the screen you're looking at, the planet beneath your feet, all of it is built from a small collection of subatomic building blocks. Electrons, protons, and neutrons. These three particles, arranged in different combinations, make up every atom of every element on the periodic table. Hydrogen is 1 proton and 1 electron. Carbon is 6 protons, 6 neutrons, and 6 electrons. Iron is 26 of each. Gold is 79 of each. The variety of the entire physical world, from water to diamond to human flesh to the iron core of the earth, comes from different arrangements of these same basic components. Every material you've ever touched, every substance you've ever tasted, every color you've ever seen, all of it traces back to electrons, protons, and neutrons arranged in different patterns. The complexity of the world is built on a remarkably simple foundation. Now, here's where things get strange. For each of these particles, there exists another particle that is almost perfectly identical to it, but with certain properties flipped. Not flipped in some vague, metaphorical sense, flipped in a precise, mathematically exact way. These flipped counterparts are called antiparticles, and together they make up what we call antimatter. Take the electron. The electron is one of the most familiar particles in physics. It carries a negative electric charge. It has a very small but specific mass, about 9.1 times 10 to the negative 31 kilograms. It has a property called spin, which is a quantum mechanical property that behaves somewhat like an intrinsic rotation, and for the electron, this spin has a value of 1/2. Now, the electron's antiparticle is called the positron. The positron has exactly the same mass as the electron. Precisely the same, not approximately, not roughly. Exactly, down to as many decimal places as we've ever been able to measure, and we've measured it with extraordinary precision. The positron also has the same spin value of 1/2. In terms of how it responds to gravity, the positron falls at the same rate as an electron. If you could build an anti-apple out of antimatter and drop it near the Earth's surface, it would fall downward, not upward. Antimatter is not anti-gravity matter. It's not some opposite version of reality that defies all familiar laws. It obeys the same fundamental laws of physics. It moves through space the same way. It experiences the same gravitational attraction. It follows the same rules of quantum mechanics. In almost every measurable way, a positron is identical to an electron. But there is one critical difference. The positron's electric charge is positive. Not negative like the electrons, but positive. Same magnitude, opposite sign. This is the defining feature of an antiparticle. The charges are reversed. If the particle carries a negative charge, its antiparticle carries a positive charge. If the particle carries a positive charge, its antiparticle carries a negative charge. The flip is exact. The magnitude of the charge is precisely the same. Only the sign changes. Now let's move to the proton. The proton sits in the nucleus of an atom. It carries a positive electric charge, equal in magnitude to the electron's charge, but opposite in sign. Its antiparticle is the antiproton, which carries a negative electric charge. Same mass as the proton, same spin, same response to gravity, but opposite charge. When physicists first produced antiprotons in a laboratory in 1955 at the Bevatron Particle Accelerator in Berkeley, California, they confirmed what theory had predicted. They slammed high-energy protons into a copper target and watched for particles emerging with the mass of a proton but a negative charge. They found them. The antiproton existed, and it behaved exactly as the equations had foretold. Same mass, opposite charge. This was a triumph of theoretical physics. The existence of the antiproton had been predicted decades before it was observed, and when the experiment was finally done, reality matched the prediction perfectly. But here's something important that many people miss. The neutron is electrically neutral. It has zero net electric charge. So you might think the neutron wouldn't have an antiparticle, because what's the opposite of zero? Zero. If the whole point of an antiparticle is having the opposite charge, and the charge is zero, then maybe there's nothing to flip. But that reasoning is wrong. The neutron does have an antiparticle. It's called the antineutron, and it was first observed in 1956, just 1 year after the antiproton. The reason the antineutron exists is that electric charge isn't the only quantum number that gets flipped when you create an antiparticle. There's something called baryon number. Protons and neutrons are both baryons, a class of particles made of 3 quarks. Every baryon has a baryon number of +1. Every antibaryon has a baryon number of -1. The neutron has baryon number +1. The antineutron has baryon number -1. They look the same in terms of electric charge, both are neutral, but they are fundamentally different particles because their internal quantum numbers are opposite. Baryon number is a conserved quantity in most physical processes, and it distinguishes baryons from antibaryons, just as clearly as electric charge distinguishes electrons from positrons. And this goes deeper still. Protons and neutrons aren't truly fundamental particles. They're composite objects, built from smaller constituents called quarks. A proton is made of 2 up quarks and 1 down quark. An antiproton is made of 2 anti-up quarks and 1 anti-down quark. A neutron is made of 1 up quark and 2 down quarks. An antineutron is made of 1 anti-up quark and 2 anti-down quarks. Each quark has its own antiquark counterpart, with opposite electric charge, opposite color charge, which is the charge associated with the strong nuclear force that binds quarks together inside protons and neutrons, and opposite baryon number. The quarks inside a proton carry fractional electric charges, which is one of the more unusual features of the quark model. An up quark has a charge of +2/3 of the electron charge. An anti-up quark has a charge of -2/3. A down quark has a charge of -1/3. An anti-down quark has a charge of +1/3. When you add up the charges of the quarks inside a proton, 2 ups and 1 down, you get +2/3, +2/3, -1/3, which equals +1, a full positive charge. When you add up the charges of the antiquarks inside an antiproton, 2 anti-ups and 1 anti-down, you get -2/3, -2/3, +1/3, which equals -1, a full negative charge. The math works out perfectly at every level of structure. Every quantum number flips, every internal label reverses. The architecture of antimatter is a precise mirror of the architecture of matter, all the way down to the quark level. So antimatter isn't just about flipping electric charge, it's about flipping all the internal quantum numbers simultaneously. Electric charge, baryon number, lepton number, color charge, strangeness, charm, bottomness, topness, all of them get reversed. The mass stays the same. The spin magnitude stays the same. The gravitational behavior stays the same. But every internal label, every quantum tag that distinguishes one type of particle from another gets flipped to its opposite value. This is a deep and exact symmetry. It's not approximate. It's not a rough correspondence. It's precise, mathematical, and has been verified experimentally with stunning accuracy across decades of particle physics research. This means you can build anti-atoms. Just as a regular hydrogen atom consists of an electron orbiting a proton, bound together by electromagnetic attraction between their opposite charges, an anti-hydrogen atom consists of a positron orbiting an antiproton. The positron carries a positive charge. The antiproton carries a negative charge. They attract each other electromagnetically, just like the electron and proton do in normal hydrogen, and they form a stable bound state, an antiatom. This isn't speculation or theoretical prediction. This has actually been done in real laboratories. In 1995, physicists at CERN, the European Organization for Nuclear Research near Geneva, Switzerland, created the first atoms of antihydrogen by combining antiprotons with positrons. These early antiatoms were moving extremely fast, close to the speed of light, which made them very difficult to study in any detail. They existed for only brief instants before encountering normal matter and annihilating. But in 2010, the Alpha experiment at CERN achieved something remarkable. They managed to trap 38 atoms of antihydrogen using carefully configured magnetic fields, holding them suspended in a vacuum for about 1/10 of a second. That doesn't sound like long, but for antimatter physics, it was groundbreaking. For the first time, scientists had confined neutral antiatoms long enough to begin studying their properties. By 2011, they could hold antihydrogen atoms for over 16 minutes. And since then, the precision of these experiments has improved dramatically. Scientists at CERN have now measured the spectral properties of antihydrogen, the specific wavelengths of light it absorbs and emits, with extraordinary accuracy. And here's what they found. Antihydrogen behaves exactly like hydrogen. Its energy levels match those of normal hydrogen. The frequencies of light it absorbs and emits are identical within the precision of measurement. The 1s to 2s transition in antihydrogen, a particularly well-studied spectral line, matches the corresponding transition in hydrogen to a precision of about 2 parts in a trillion. 2 parts in a trillion. That's like measuring the distance from the Earth to the Sun and being accurate to within a fraction of a millimeter. The physics of antiatoms is indistinguishable from the physics of normal atoms. This is a profound result. It tells us that an antiatom built from antiparticles produces the same spectral lines, the same chemistry, the same physical behavior as a normal atom. If you had a block of anti-iron, it would look like iron. It would have the same silvery metallic sheen. It would conduct electricity the same way. It would have the same density, the same melting point, the same crystal structure. You could not distinguish it from regular iron by any measurement of its material properties. The only way to tell would be to bring it into contact with normal matter, and then both would annihilate in a catastrophic release of energy. You could, in principle, build an entire anti-world out of antimatter. Anti-atoms forming anti-molecules, anti-molecules forming anti-water, anti-rock, anti-air, anti-chemistry driving anti-biology on anti-planets, orbiting anti-stars in anti-galaxies. An entire cosmos built from antimatter would look exactly like ours. The anti-stars would burn through the same nuclear fusion processes, converting anti-hydrogen into anti-helium and releasing energy in the form of photons, which are their own antiparticles, and therefore identical in both matter and antimatter scenarios. The antiplanets would have the same geological processes. Anti-water would freeze at the same temperature and boil at the same temperature. Anti-DNA would carry the same genetic information using the same chemical mechanisms. And if intelligent beings existed on such an anti-world, made entirely of antimatter, they would observe the same physics, the same chemistry, the same physical laws that we do. They would have no way to tell, from internal experiments alone, that they were made of antimatter rather than matter. Their physics textbooks would read identically to ours. Their periodic table would look the same. Their stars would shine the same way. Their biologists would study the same molecular processes. From the inside, a matter universe and an antimatter universe are indistinguishable. This near-perfect symmetry between matter and antimatter is one of the most striking features of the laws of physics. The universe, at the level of its fundamental equations, doesn't appear to prefer one over the other. Both are equally valid. Both produce the same structures, the same complexity, the same chemistry. The equations of the standard model of particle physics, which describe all known fundamental particles and 3 of the 4 fundamental forces, are almost perfectly symmetric between particles and antiparticles. Almost. That word almost is going to become critically important later in our story. But for now, let's appreciate the depth and beauty of the symmetry itself. Matter and antimatter are mirror images of each other, equally real, equally valid, equally capable of building complex structures, complex chemistry, and potentially complex life. Now, antimatter is not some exotic substance confined to particle accelerators and science fiction. It's produced naturally all the time, all around you, even inside you. Certain types of radioactive decay produce positrons. There's a specific type of nuclear decay called beta plus decay, where a proton inside an unstable nucleus converts into a neutron and releases a positron along with a neutrino. This happens in nature constantly. The potassium-40 isotope found naturally in bananas, in soil, in rocks, and in your own bones can in very rare instances undergo a type of decay that emits positrons. Only about 1 in every 100,000 potassium-40 decays takes this path, but it does happen. Your body also contains trace amounts of other isotopes like carbon-11 and nitrogen-13 produced by cosmic ray interactions, and these too emit positrons when they decay. You are producing antimatter inside your own body at this very moment. Not much of it, a trivially tiny amount. The positrons travel less than a millimeter through your tissue before encountering an electron and annihilating, but the process is real. Antimatter is not alien to your body. It's part of the natural radioactive landscape that exists inside every living thing on Earth. Cosmic rays, high-energy particles from deep space that rain down on Earth continuously, strike atoms in the upper atmosphere and produce showers of secondary particles. Some of these secondary particles are positrons and antiprotons. These antimatter particles exist briefly, traveling through the atmosphere at tremendous speeds before encountering ordinary matter and annihilating. The Earth is constantly being sprinkled with tiny amounts of antimatter from space. Lightning bolts produce positrons through nuclear reactions triggered by the intense electric fields inside thunderstorms. The Sun produces antimatter through various nuclear processes in its core. Antimatter is woven into the natural world at every scale, from the interior of your body to the surface of the Sun to the depths of interstellar space. Antimatter is also used in medicine. This is probably the most practical, most routine, most everyday application of antimatter that exists today. Positron emission tomography, which you probably know as a PET scan, works by injecting a patient with a radioactive tracer. The most common tracer is a modified sugar molecule called fluorodeoxyglucose, labeled with a radioactive isotope of fluorine, fluorine-18. This isotope undergoes beta plus decay with a half-life of about 110 minutes, emitting positrons as it decays. When those positrons travel a short distance through the patient's body tissue, usually just a millimeter or 2, they encounter electrons in the surrounding atoms. And when a positron meets an electron, both particles annihilate. They cease to exist. In their place, two gamma-ray photons appear, flying off in nearly exactly opposite directions. Detectors arranged in a ring around the patient pick up these photon pairs. When two detectors on opposite sides of the ring register gamma-ray photons at almost exactly the same time, within a few nanoseconds of each other, the system knows that an annihilation event occurred somewhere along the line connecting those two detectors. By recording millions of these coincidence events over the course of the scan, typically 20 to 40 minutes, the system builds up a detailed three-dimensional map of where the tracer has concentrated inside the body. Cancer cells tend to consume more sugar than normal cells because they're growing and dividing rapidly. So areas with high tracer concentration, which show up as bright spots on the PET image, often indicate tumors or metastatic disease. PET scans are used routinely in diagnosing cancer, staging its spread, studying brain function in conditions like Alzheimer's disease, evaluating heart disease, and monitoring how patients respond to chemotherapy and radiation treatment. Every single bright spot on a PET scan image represents countless individual matter-antimatter annihilation events happening inside a patient's body. Millions of moments where a positron met an electron and both vanished in a flash of gamma radiation. Antimatter annihilation, the most energetically complete process in all of physics, happening inside a human being in a hospital. As a routine diagnostic procedure, this technology has been in widespread clinical use since the early 1990s. There is nothing theoretical about antimatter. It's saving lives right now. In 2023, the Alpha-G experiment at CERN performed another landmark measurement. They released anti-hydrogen atoms inside a vertical chamber and carefully tracked which direction they fell. The result confirmed what most physicists had long expected but had never directly verified. Anti-hydrogen falls downward in a gravitational field. It is attracted by gravity in exactly the same way as ordinary hydrogen. This ruled out exotic theories that had proposed antimatter might experience repulsive gravity, falling upward rather than downward. It doesn't. Antimatter responds to gravity normally. It's attracted to mass. It falls toward the center of the Earth, just like everything else. So let's take stock of what we now understand. Every particle of matter has a corresponding antiparticle of antimatter. The antiparticle has the same mass, the same spin, the same gravitational behavior, but opposite electric charge and opposite internal quantum numbers like baryon number and lepton number. Antiatoms built from antiparticles behave identically to normal atoms, producing the same spectral lines, the same chemistry, the same physical behavior, verified experimentally to extraordinary precision. The laws of physics, at the fundamental level, treat matter and antimatter with near-perfect symmetry. Antimatter is produced naturally in radioactive decay, cosmic ray interactions, lightning, and stellar processes. It's created routinely in particle accelerators. It's used daily in hospitals for medical imaging. It responds to gravity normally. It's not exotic. It's not fictional. It's a real, well-understood, experimentally verified part of the physical world that surrounds us. And yet, despite all of this, despite this near-perfect symmetry between matter and antimatter, there is virtually no antimatter in the observable universe. This is one of the strangest and most unsettling facts in all of science. Everywhere astronomers look, in every direction, at every distance, they see matter. Stars are made of matter. Planets are made of matter. Moons and asteroids are made of matter. The gas clouds between stars are made of matter. The thin plasma between galaxies is made of matter. We have searched carefully and methodically for evidence of large-scale antimatter structures, anti-stars shining with anti-light, anti-galaxies spinning through space, and we have found nothing, not a trace. If there were regions of the universe made of antimatter, we would expect to see a distinctive signature at the boundaries where matter regions and antimatter regions meet. At those boundaries, particles from the matter side would inevitably drift across into the antimatter region, and particles from the antimatter side would drift the other way. When they met their counterparts, they would annihilate, and that annihilation would produce gamma rays with a very specific, unmistakable energy. Electron-positron annihilation produces gamma-ray photons with an energy of exactly 511 kiloelectron volts. This energy corresponds to the rest mass of an electron converted entirely to radiation. It's a distinctive spectral line, a fingerprint that would be impossible to miss with modern gamma-ray telescopes. If matter-antimatter boundaries existed anywhere in the observable universe, even at the scale of galaxy clusters separated by vast cosmic voids, we would see this 511 kiloelectron volt emission glowing from those boundaries. We have looked with dedicated gamma-ray satellites like the Fermi Gamma-Ray Space Telescope, scanning the entire sky with sensitive instruments tuned precisely to this energy range. We don't see it. The gamma-ray sky shows no evidence of large-scale matter-antimatter boundaries anywhere. As far as every observation can determine, matter dominates everywhere, in every galaxy cluster, in every supercluster, in every direction, out to the farthest reaches of the observable universe, roughly 46 billion light-years in every direction. This is deeply, fundamentally puzzling. The laws of physics treat matter and antimatter with near-perfect symmetry. There is no obvious reason written into the equations why the universe should prefer one over the other. It would be like flipping a perfectly balanced, perfectly fair coin 10 billion trillion times and getting heads every single time. The probability of that happening by chance is so close to zero that it might as well be impossible. The symmetry says it shouldn't happen. Something must have broken the symmetry. Something must have tipped the cosmic scales ever so slightly toward matter and away from antimatter. And whatever that something was, it determined the fate of the entire universe. Think about what this means for you, personally. You exist because the universe is made of matter. Every atom in your body, every atom on Earth, every atom in every star, in every galaxy, in the observable universe, all of it is matter. And all of the antimatter that the laws of physics say should have been produced in exactly equal amounts is simply gone, vanished, nowhere to be found across the entire observable cosmos. The universe created both in equal measure, in unimaginable quantities, and somehow only one side survived. The other side was almost entirely erased. Understanding how that happened, understanding the mechanism that allowed matter to win this cosmic contest while antimatter lost, requires us to look at what happens when the two actually meet. Because when matter encounters antimatter, the result is not gentle, it is not gradual, it is the most violent, most complete, most total form of destruction that the laws of physics permit. And understanding that destruction is the key to understanding why the universe exists at all. When a particle encounters its antiparticle, something violent happens. Something absolute. The two particles don't bounce off each other. They don't merge into a heavier particle. They don't coexist side by side in some uneasy truce. They annihilate. Both particles cease to exist entirely. Their mass, every last fraction of it, is converted into energy. Pure energy. Usually in the form of high-energy photons called gamma rays. There is nothing left behind. No residue, no fragments, no ash. The particles simply vanish from the physical world, and in their place, there is light. This process is called matter-antimatter annihilation, and it is the most complete form of destruction that physics allows. Not even nuclear weapons come close to this level of total conversion. When matter meets antimatter, 100% of the mass becomes energy. Nothing is wasted. Nothing survives. The transformation is absolute. Let's take the simplest and most well-understood case. An electron meets a positron. The electron has a tiny mass. The positron has the same tiny mass. When they come close enough to interact, both masses disappear. What appears in their place is a pair of gamma-ray photons, high-energy particles of light that fly off in nearly exactly opposite directions. The total energy of those two photons is precisely equal to the total energy that was contained in the mass of the electron and positron, plus whatever kinetic energy they had when they collided. Not approximately equal. Precisely equal. Energy is conserved with absolute exactness. The relationship between mass and energy in this process is governed by the most famous equation in all of physics, E = mc², Einstein's equation. Published in 1905 as a consequence of his theory of special relativity. This equation tells you that mass and energy are not separate things. They are two forms of the same underlying quantity. Mass can be converted into energy, and energy can be converted into mass. The conversion factor between them is the speed of light squared. And the speed of light is an enormous number. About 300,000 kilometers per second. When you square that, you get 9 × 10⁻16 in metric units. That's a 90 followed by 15 zeros. This means that even a tiny amount of mass contains an extraordinary amount of energy. A paperclip, if you could convert its entire mass to energy, would release enough energy to power a city for years. The amount of energy locked inside matter is staggering, far beyond anything our everyday experience would suggest. In matter-antimatter annihilation, E = mc² operates at 100% efficiency. The entire rest mass of both particles is converted to energy. No other process in nature achieves this. Let me put that in perspective by comparing annihilation to other energy-releasing processes. Chemical reactions, the kind that power your car engine or heat your stove, release energy by rearranging the bonds between atoms. When you burn gasoline, carbon and hydrogen atoms in the fuel react with oxygen atoms in the air, forming carbon dioxide and water. Energy is released because the new bonds are more stable than the old ones. But the total mass of the products is almost exactly the same as the total mass of the reactants. The difference is so tiny it's essentially unmeasurable with ordinary instruments. Chemical reactions convert roughly 1/10000000% of the reactant mass into energy. That's 10 orders of magnitude less than 1%. Chemical energy is real and useful. It powers modern civilization. But in terms of mass to energy conversion, it barely registers. Nuclear fission, the process used in nuclear power plants and atomic bombs, does significantly better. When a uranium-235 nucleus absorbs a neutron and splits into two smaller nuclei, the combined mass of the products is slightly less than the mass of the original uranium nucleus plus the neutron. That missing mass has been converted to energy. The conversion efficiency is about 0.1%. 1/10 of the mass becomes energy. That sounds small, but because c² is so large, even this tiny fraction produces enormous amounts of energy. A single kilogram of uranium-235 undergoing complete fission releases about 82 terajoules of energy. That's roughly equivalent to 20,000 tons of TNT. This is why nuclear weapons are so devastating, and why nuclear power plants can generate electricity for entire cities from relatively small amounts of fuel. Nuclear fusion, the process that powers the sun and all other stars, is more efficient still. When 4 hydrogen nuclei fuse together to form one helium nucleus deep in the sun's core, about 0.7% of the original mass is converted to energy, 0.7%. This is 7 times more efficient than fission. The sun converts about 4 million tons of mass into energy every single second through this process, and it has been doing so for about 4.5 billion years. It will continue for another 5 billion years or so before it exhausts its hydrogen fuel. Fusion is the most powerful energy source that occurs naturally in the universe on a large scale. It's what makes stars shine. It's what makes life on Earth possible, and it converts less than 1% of mass to energy. Matter-antimatter annihilation converts 100%, not 0.1%, not 0.7%, 100%. Every last bit of mass becomes energy. Nothing is left over. If you could take 1 kilogram of matter and annihilate it with 1 kilogram of antimatter, the energy released would be approximately 1.8 times 10 to the 17 joules. That's about 180 petajoules. To put that in a more relatable context, that's roughly equivalent to the energy released by a 43 megaton nuclear weapon from just 2 kilograms of material total. The Tsar Bomba, the most powerful nuclear weapon ever detonated by humans, released about 50 megatons of energy. That device weighed approximately 27 metric tons. Matter-antimatter annihilation could nearly match that energy output from 2 kilograms. The energy density of antimatter as a fuel source is almost incomprehensibly high. It is, by a wide margin, the most energy-dense substance that the laws of physics permit. This is why antimatter has captured the imagination of science fiction writers and engineers for decades. It's the ultimate fuel, the theoretical maximum. If you could somehow produce antimatter in large quantities, store it safely, and release its energy in a controlled way, you would have a power source that dwarfs everything else humans have ever conceived. A few grams of antimatter could power a spacecraft on an interplanetary journey. A few kilograms could theoretically propel a ship to a significant fraction of the speed of light. The energy is there, locked in the equation, waiting to be released. But there are enormous practical problems, and they all stem from the same fundamental fact that makes annihilation so powerful. Antimatter annihilates on contact with any matter whatsoever. It doesn't need to be heated. It doesn't need to be compressed. It doesn't need a trigger or a detonator or any special conditions. The moment an antiparticle gets close enough to a particle, they annihilate. This is not a choice the particles make. It's not a reaction that requires activation energy like a chemical reaction. It happens spontaneously and immediately whenever the two particles encounter each other. This means you cannot store antimatter in any ordinary container. If you put antihydrogen in a glass jar, the anti-atoms would touch the glass walls, annihilate with the silicon and oxygen atoms in the glass, and release a burst of gamma radiation. The antimatter would be gone in an instant, and the container would be damaged or destroyed. You can't use metal containers, plastic containers, ceramic containers, or containers made of any material whatsoever, because all materials are made of matter, and antimatter annihilates with matter. Period. No exceptions. The only way to store charged antimatter particles, like antiprotons or positrons, is to suspend them in a vacuum using electromagnetic fields. A device called a penning trap uses a combination of electric and magnetic fields to confine charged particles in a small region of space without them ever touching the walls of the device. The particles float in the vacuum, held in place by invisible electromagnetic forces, never contacting any material surface. Penning traps work, and they've been used for decades to store small numbers of antiprotons and positrons. But the quantities are minuscule. We're talking about thousands or millions of individual particles, which sounds like a lot until you realize that a single gram of matter contains about 6 times 10 to the 23 atoms. The total amount of antimatter that has ever been produced by all the particle accelerators on Earth combined, if you gathered every last antiproton and positron ever created in every laboratory in every country, the total would amount to less than 20 nanograms. 20 billionths of a gram. If you annihilated all of that antimatter with an equal amount of normal matter, the energy released would not be enough to boil a cup of water. Storing neutral anti-atoms like antihydrogen is even harder because they have no net electric charge, so you can't use electric fields to hold them. Instead, the alpha experiment at CERN uses an extremely clever arrangement of magnetic fields that exploits the tiny magnetic moment of the antihydrogen atom. The anti-atom acts like a very weak magnet, and if you create a magnetic field that's weaker in the center and stronger at the edges, the anti-atom will be gently pushed toward the center, trapped in a magnetic bottle. This works, but only for anti-atoms that are moving very slowly, meaning they've been cooled to temperatures just a fraction of a degree above absolute zero. And even then, the trap can only hold a small number of anti-atoms at a time. The current record is holding about 1,000 antihydrogen atoms simultaneously for several hours. That's an impressive scientific achievement, but it's an astronomically tiny amount of antimatter. The fundamental difficulty is this. The same property that makes antimatter so energetically valuable, its tendency to annihilate completely on contact with matter, is exactly what makes it nearly impossible to store in useful quantities. It's a perfect catch-22. The better the fuel, the harder it is to keep in a tank. Now, let's talk about what actually happens during an annihilation event in more physical detail, because the process is different depending on which particles are involved. For the simplest case, electron-positron annihilation, the process is clean and straightforward. The electron and positron meet, both vanish. 2 gamma-ray photons are produced, each with an energy of 511 kilo-electron volts. This energy corresponds exactly to the rest mass energy of an electron, or equivalently a positron, calculated using E equals mc squared. The 2 photons fly off in almost exactly opposite directions, which is required by conservation of momentum. If the electron and positron were both at rest when they met, the photons go in precisely opposite directions. If they had some motion, the angles adjust slightly, but they're always close to 180 degrees apart. The 511 kilo-electron volt energy of these gamma-ray photons is a distinctive signature. It's like a fingerprint that identifies electron-positron annihilation wherever it occurs. Gamma-ray telescopes orbiting Earth can detect this specific energy and use it to map where positron annihilation is happening in the universe. We detect this emission from the center of our own galaxy, the Milky Way, where positrons are produced by various astrophysical processes and then annihilate with electrons in the interstellar gas. The 511 kilo-electron volt line is one of the strongest gamma-ray signals from the galactic center. For heavier particles, the process is more complex. When a proton meets an antiproton, you might expect a clean annihilation into photons, just like the electron-positron case, but with more energy. But that's not what happens. Remember, protons and antiprotons are not fundamental particles. They're made of quarks and antiquarks, bound together by gluons, the force-carrying particles of the strong nuclear force. When a proton and antiproton meet, the quarks and antiquarks inside them interact through the strong force. The result is not a simple pair of gamma rays. Instead, the annihilation produces a spray of particles, primarily pions. Pions are particles made of 1 quark and 1 antiquark. They come in 3 varieties: positive pions, negative pions, and neutral pions. A typical proton-antiproton annihilation at low energies produces about 5 pions on average, though the exact number varies from event to event. These pions are unstable. They don't last long. Neutral pions have an extraordinarily short lifetime of about 8.4 times 10 to the negative 17 seconds. That's 84 quadrillionths of a second. Almost instantly after being created, they decay into 2 gamma-ray photons each. Charged pions live longer, about 26 nanoseconds, which is still incredibly brief by human standards, but long enough for the pions to travel several meters through space before they decay. Charged pions decay into muons and neutrinos. The muons are also unstable, living about 2.2 microseconds before decaying into electrons or positrons plus neutrinos. So the annihilation of a proton and antiproton produces a cascade of particles. First pions, then muons and gamma rays, then electrons, positrons, neutrinos, and more gamma rays. Eventually, the electrons and positrons annihilate with each other, producing yet more gamma rays. The neutrinos escape, carrying away some of the energy. But in the end, most of the original mass energy ends up as gamma ray photons. The process just takes a few more steps than the clean electron-positron case. The end result is the same fundamental transformation. Mass becomes energy, particles become light, matter and antimatter are converted entirely into radiation. The gamma rays produced by annihilation are extremely dangerous to biological organisms. They are far more energetic than medical X-rays, and they penetrate deeply into matter. A burst of gamma radiation from a large-scale annihilation event would be lethal at considerable distances. The radiation would damage DNA, destroy cellular structures, and cause severe radiation sickness or immediate death depending on the dose. There would be no visible explosion in the traditional sense, no mushroom cloud of fire and debris, because gamma rays are invisible to the human eye. There would simply be a blinding flash of energy at wavelengths we cannot see, a burst of deadly radiation expanding outward at the speed of light, and then silence. Anything nearby would be irradiated. Anything close enough would simply cease to function biologically. Now, here's where the physics becomes truly remarkable. Everything I've just described, the annihilation of matter and antimatter into energy, works perfectly well in reverse. Just as a particle and antiparticle can annihilate to produce photons, photons with sufficient energy can spontaneously produce a particle-antiparticle pair. This reverse process is called pair production, and it is one of the most extraordinary phenomena in all of physics. Energy becomes matter, light becomes substance. Something intangible and massless transforms into something with mass, with charge, with all the properties of solid reality. It is, in a very real sense, creation from nothing material, pure energy condensing into particles that have weight, that take up space, that interact with their surroundings. For pair production to occur, a gamma-ray photon must have at least enough energy to account for the combined rest mass of the particle and antiparticle it creates. For an electron-positron pair, the minimum photon energy required is about 1.02 million electron volts, which is twice the rest mass energy of an electron. For a proton-antiproton pair, much more energy is needed because protons are about 1,836 times more massive than electrons. You need a photon with at least about 1.88 billion electron volts. The more massive the particles you want to create, the more energetic the photon must be. There's one additional requirement. Pair production can't happen with a single photon all by itself in empty space. Conservation of momentum forbids it. A photon carries momentum, and if it converted into a particle-antiparticle pair, the momentum of the photon couldn't be distributed between the two new particles in a way that satisfies both conservation of energy and conservation of momentum simultaneously. So pair production requires a nearby third body, typically an atomic nucleus, to absorb some of the recoil momentum. In practice, this means pair production happens when a high-energy gamma ray passes close to a heavy atom. The nucleus provides the momentum balance, and the photon converts into a particle-antiparticle pair. The key insight about pair production is this: it always creates matter and antimatter in exactly equal amounts. Always, without exception. You never get just an electron from pair production. You always get an electron and a positron together. You never get just a proton. You always get a proton and an antiproton. This is because the quantum numbers must balance. The photon has 0 electric charge, 0 baryon number, 0 lepton number. The particle-antiparticle pair also has 0 total charge, 0 total baryon number, and 0 total lepton number, because the quantum numbers of the particle and antiparticle cancel each other perfectly. The books must balance. Conservation laws demand it. This perfect pairing is not a technicality. It is going to become the central mystery of our story. Because if every process that creates matter from energy must simultaneously create an equal amount of antimatter, then how can the universe be made overwhelmingly of matter? Where did all the antimatter go? How did the perfect balance get broken? But let's stay with the physics for a moment longer, because the symmetry between annihilation and pair production reveals something deep about the nature of reality. These two processes are mirror images of each other. In annihilation, particles with mass are converted into massless photons. In pair production, massless photons are converted into particles with mass. Matter becomes light. Light becomes matter. The two processes are in a constant dynamic equilibrium wherever the conditions allow both to occur. This equilibrium exists because of how quantum field theory works at the most fundamental level. In quantum field theory, particles are not tiny solid balls zipping through space. They are excitations of underlying quantum fields. The electron field permeates all of space. When this field is excited in a particular way, that excitation appears as an electron. When it's excited in the opposite way, that excitation appears as a positron. When an electron and positron annihilate, their excitations cancel out in the electron field, and the energy transfers to the electromagnetic field, appearing as photon excitations. When pair production occurs, the process reverses. Energy in the electromagnetic field transfers to the electron field, creating both types of excitation simultaneously. Think of it like a pond with two types of ripples going up and ripples going down. If an upward ripple meets a downward ripple of the same size, they cancel out and the energy disperses as smaller waves across the water. That's annihilation. Conversely, if enough energy is concentrated in one spot, it can create an upward ripple and a downward ripple simultaneously. That's pair production. The ripples always come in matched pairs because the underlying physics demands it. You can't create one without the other. This framework also explains why annihilation happens spontaneously whenever a particle encounters its antiparticle. The excitations are opposite. When they occupy the same region of space, they naturally cancel. There's no barrier to this cancellation, no activation energy needed, no threshold to overcome. It simply happens because the excitations are inherently complementary. They fit together like a key in a lock, and when they meet, both disappear. The energy has to go somewhere because energy is always conserved, so it appears as photons, but the original excitations, the particle and the antiparticle, are gone. This also means that in any environment where there is enough energy, matter and antimatter are constantly being created and destroyed. The vacuum of space itself is not truly empty. Quantum field theory tells us that the vacuum seethes with virtual particle-antiparticle pairs, particles that pop into existence from nothing and annihilate back into nothing almost instantly. These virtual pairs exist for incredibly brief moments, too short to be directly observed individually, but their collective effects are measurable. The Casimir effect, a tiny force between two closely spaced metal plates in a vacuum, arises because virtual particles exist between and around the plates. The Lamb shift, a small difference in energy levels of the hydrogen atom that can't be explained by simple quantum mechanics, arises because the electron in the atom interacts with virtual particle-antiparticle pairs flickering in and out of existence around it. The vacuum is not empty. It's alive with the constant creation and destruction of matter and antimatter at quantum scales. In environments with extreme energy, the creation and destruction become real rather than virtual. Inside particle accelerators, where protons are smashed together at nearly the speed of light, the energy of the collision is so high that it routinely creates particle-antiparticle pairs. This is how particle accelerators discover new particles. You put in enough energy, and that energy materializes as mass, always in particle-antiparticle pairs. Every new particle discovered at the Large Hadron Collider at CERN was produced alongside its antiparticle. The top quark was produced with the anti-top quark. The Higgs boson, while it is its own antiparticle, was produced through processes that conserve all quantum numbers precisely. Near black holes, where gravitational fields are so intense that space-time itself is warped, the energy of the gravitational field can produce particle-antiparticle pairs through a process related to pair production. This is thought to be the mechanism behind Hawking radiation, the theoretical prediction that black holes slowly evaporate by emitting particles. The intense gravitational field near the event horizon creates virtual particle-antiparticle pairs, and occasionally one particle falls into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting particles and slowly losing mass. The energy to create these particles comes from the gravitational field of the black hole itself. And in the very early universe, in the first fractions of a second after the Big Bang, the temperature and energy density was so extraordinarily high that pair production was happening everywhere, constantly, at a rate that is almost impossible to comprehend. The entire universe was a seething plasma of particles and antiparticles being created from pure energy and annihilating back into pure energy, trillions upon trillions of times per second in every cubic centimeter of space. Matter was being created and destroyed in equal amounts on a cosmic scale. That primordial chaos is where we're headed next. Because what happened in those first moments, in that unimaginably hot and dense environment where matter and antimatter were being forged from pure energy in perfectly equal quantities, determined the fate of everything. Every atom that would ever exist, every star that would ever shine, every planet that would ever form, every living thing that would ever draw breath, all of it depended on what happened in those first fractions of a second. The laws of physics demanded perfect symmetry. Equal matter, equal antimatter. And if that symmetry had held, if the balance had remained perfect, the matter and antimatter would have annihilated each other completely as the universe cooled. Nothing would have survived except light. The universe would be a vast, expanding sea of radiation with no atoms, no structures, no complexity, and no life, forever. But the symmetry didn't hold. Something broke it. Something incredibly small, almost imperceptibly small, tipped the balance. And that tiny imperfection in the laws of physics made everything possible. To understand what that imperfection was, we first need to understand what happened in those first moments of existence, when the universe was a furnace of creation and destruction operating on a scale that dwarfs anything we can experience or even properly imagine. We need to go back to the very beginning, to the Big Bang itself, to the moment when matter and antimatter were born together in equal measure from the fire of creation and then very nearly destroyed each other completely. The Big Bang. Roughly 13.8 billion years ago, the universe began in a state of unimaginable energy density. We don't know what happened at the very first instant, at time zero itself, because our current theories of physics break down at those extreme conditions. The temperatures and densities were so far beyond anything we can recreate in a laboratory that the known laws of physics simply stop making reliable predictions. General relativity, Einstein's theory of gravity, predicts a singularity, a point of infinite density and infinite temperature. But most physicists believe this singularity is not real. It's a sign that the theory is incomplete, that something else, some deeper theory of quantum gravity that we haven't yet discovered, takes over at the very earliest moments. We don't have that theory yet. So the true origin, the actual moment of creation, if there was one, remains hidden from us behind a wall of unknown physics. But we can describe what happened from very shortly after the beginning. From about 1/1,000,000,000 of a second onward, our theories are on solid ground. They've been tested against observations of the cosmic microwave background, the abundances of light elements, the large-scale structure of the universe, and countless other data points. The predictions match the observations with remarkable precision. We may not know what happened at time zero, but we know with considerable confidence what the universe was like a trillionth of a second later, and what it was like was almost incomprehensibly hot and dense. In the first moments after the Big Bang, the temperature of the universe was measured in trillions of degrees, not millions, not billions, trillions. At these temperatures, the distinction between energy and matter essentially dissolved. Energy was constantly converting into matter, and matter was constantly converting back into energy. Every time a particle and antiparticle found each other, they annihilated back into photons, and those photons immediately had enough energy to create new pairs. The cycle was endless, self-sustaining, furious in its intensity. This wasn't happening in some small region of space. It was happening everywhere. The entire observable universe, everything that would one day become every galaxy and every star and every planet, was compressed into a much smaller volume. And every point in that volume was a cauldron of creation and destruction operating at energies that no particle accelerator on Earth has ever achieved or likely ever will. Now, here is the critical point that underpins the entire mystery of antimatter. As we discussed, pair production always creates matter and antimatter in exactly equal amounts. This is an absolute requirement of the conservation laws. For every quark created from the energy of the early universe, an antiquark was also created. For every electron, a positron. For every neutrino, an antineutrino. So in the very early universe, there was exactly as much antimatter as matter. The universe was perfectly balanced, perfectly symmetric. For every proton that existed, there was an antiproton somewhere nearby. For every electron, a positron. The cosmos was a democracy of matter and antimatter, with neither side holding any advantage whatsoever. This is not speculation. We can calculate what this early plasma was like using well-tested physics. The equations of quantum field theory at high temperatures tell us precisely what the particle content of the universe was at different temperatures. At temperatures above about 10 trillion degrees, which the universe exceeded in its first microsecond of existence, the plasma contained roughly equal numbers of quarks, antiquarks, electrons, positrons, muons, antimuons, neutrinos, antineutrinos, and photons, all in thermal equilibrium, all constantly interconverting. The universe was a hot soup of everything, with matter and antimatter represented in precisely equal proportions. As the universe expanded, it cooled. This is a straightforward consequence of expansion, and is one of the most basic predictions of Big Bang cosmology. When a gas expands, it cools. This is the same principle that makes a can of compressed air feel cold when you spray it. The molecules spread out, the energy density drops, and the temperature falls. The same thing happened to the universe as a whole, just on a vastly larger scale. As space itself expanded, the energy density of the universe decreased. The temperature dropped. And as the temperature dropped, the energy available for pair production decreased as well. This is where things begin to change. Pair production requires a minimum amount of energy to create each type of particle. Heavier particles require more energy than lighter ones. Creating a proton-antiproton pair requires about 1,836 times more energy than creating an electron-positron pair, because protons are that much more massive than electrons. As the universe cooled below certain critical temperatures, it crossed energy thresholds. Below each threshold, the universe no longer had enough thermal energy to produce a particular type of particle-antiparticle pair. The first threshold to be crossed involved the heaviest particles. Top quarks and anti-top quarks, the heaviest known fundamental particles with masses about 184 times the mass of a proton, could no longer be produced once the temperature dropped below a certain point. This happened very early, within a trillionth of a second after the Big Bang. Existing top quarks and anti-top quarks decayed almost immediately because they're extremely unstable, and no new ones were created to replace them. They vanished from the universe's inventory. Then the same thing happened for bottom quarks and anti-bottom quarks, then charm quarks and anti-charm quarks, then strange quarks and anti-strange quarks. One by one, as the temperature fell, the heavier particle species froze out. They could no longer be created from the available thermal energy, and the existing ones decayed or annihilated. By about 10 microseconds after the Big Bang, when the temperature had dropped to roughly 2 trillion degrees, something dramatic happened. The remaining quarks and antiquarks, mostly up quarks, down quarks, and their antiquark counterparts, became confined inside protons, antiprotons, neutrons, and antineutrons through a process called hadronization. The strong nuclear force, which binds quarks together, became dominant at these lower energies, locking the quarks into composite particles. At this point, the universe contained roughly equal numbers of protons and antiprotons, neutrons and antineutrons, along with electrons, positrons, neutrinos, antineutrinos, and a vast sea of photons. The temperature was still enormously high by any human standard, trillions of degrees, but it was no longer high enough to create new proton-antiproton pairs from thermal energy. The protons and antiprotons that existed were the last generation. No more would be created. And now, with pair production of heavy particles shut down, the remaining protons and antiprotons began finding each other and annihilating. This annihilation was thorough, devastatingly thorough. Protons and antiprotons attracted each other electromagnetically, the proton's positive charge pulling toward the antiproton's negative charge, and when they met, both vanished in a spray of pions that quickly decayed into gamma rays, neutrinos, electrons, and positrons. The universe was destroying its own matter and antimatter content on a colossal scale. Billions of protons and antiprotons annihilating every second in every tiny region of space. The energy released by all this annihilation added to the photon bath, the background radiation that filled the universe. With each annihilation event, 2 particles of matter disappeared and were replaced by pure radiation. This annihilation epoch continued as the universe expanded and cooled further. The protons and antiprotons that hadn't yet found each other were spread farther apart by the expansion of space, which slowed the annihilation rate. But the rate was still enormous. Over the course of the first few seconds, the vast majority of the protons and antiprotons that had existed in the universe found partners and annihilated. The same process occurred slightly later for electrons and positrons. As the temperature dropped below about 5 billion degrees, roughly 1 second after the Big Bang, the universe could no longer produce electron-positron pairs from thermal energy. The remaining electrons and positrons began annihilating in the same catastrophically thorough fashion. Electron after electron met positron after positron, and both vanished into pairs of gamma-ray photons. By the time this process was complete, most of the matter and antimatter in the universe had been destroyed. The annihilation was almost total, almost complete. Nearly every particle found an antiparticle partner and was converted into radiation. The universe transitioned from a state dominated by matter and antimatter in equal proportions to a state dominated overwhelmingly by radiation, by photons, by light. The particles were gone, almost all of them, converted into the pure energy of a universe filled with light. Now, if the annihilation had been perfectly complete, if every particle had found an antiparticle partner and annihilated, the result would have been a universe containing nothing but photons, nothing but light. No protons, no neutrons, no electrons, no atoms, no molecules, no chemistry, no stars, no planets, no oceans, no mountains, no trees, no animals, no people, nothing. Just an expanding, cooling sea of electromagnetic radiation growing dimmer and dimmer as the universe expanded. A universe of pure light fading slowly toward absolute darkness forever. This is what the mathematics predicts if you start with perfect symmetry. Equal matter, equal antimatter, total annihilation, nothing left but radiation. No structures can form from pure radiation. Photons don't clump together under gravity the way matter does. They don't form atoms or molecules. They don't condense into stars. They just expand and cool forever. But that is not what happened. Something else occurred. Something subtle. Something tiny. Something that physicists have spent decades trying to fully understand. The annihilation was not perfectly complete. It was almost complete. Overwhelmingly, staggeringly, almost inconceivably close to complete. But not quite. For some reason, the universe produced very slightly more matter than antimatter. Just a tiny bit more, the slightest possible excess. And when the great annihilation was over, when essentially all the antimatter had found matter partners and both had been converted to light, there was a little bit of matter left over, a residue, a remainder, an orphan population of particles that had no antimatter partners to annihilate with, simply because there weren't enough antiparticles to go around. How small was this excess? We can measure it. The cosmic microwave background radiation, the afterglow of the Big Bang that fills the entire sky, tells us exactly how thorough the annihilation was. This radiation was first detected in 1965 by Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey. They were working with a sensitive microwave antenna and found a persistent background signal coming from every direction in the sky. No matter where they pointed the antenna, the signal was there, uniform and constant. At first, they thought it was noise. They checked everything. They cleaned pigeon droppings off the antenna. They tested every component. The signal wouldn't go away. Eventually, they realized they were detecting something fundamental, the remnant radiation from the early universe. They received the Nobel Prize in Physics in 1978 for this discovery. Today, we've measured the cosmic microwave background with exquisite precision, using satellite missions like COBE, launched in 1989, WMAP, launched in 2001, and Planck, launched in 2009. These measurements tell us that the CMB has a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. It has an almost perfectly uniform spectrum consistent with radiation from a thermal source, exactly as the Big Bang theory predicts. And it contains tiny fluctuations, variations of about 1 part in 100,000 from point to point across the sky, which correspond to slight density variations in the early universe that would eventually grow into the galaxies and galaxy clusters we see today. The total number of photons in the cosmic microwave background is enormous. There are about 412 CMB photons in every cubic centimeter of space, everywhere in the universe. That adds up to an almost incomprehensibly large total number. These photons are the remnants of all the annihilation events that occurred in the first seconds after the Big Bang. Every proton that annihilated with an antiproton, every electron that annihilated with a positron, contributed its energy to this sea of radiation that still fills the cosmos 13.8 billion years later. Now here's the crucial measurement. When we compare the number of photons in the cosmic microwave background to the number of baryons, protons, and neutrons in the universe today, we find a ratio of roughly 1.5 billion to 1. For every proton or neutron that exists in the universe today, there are over 1 billion CMB photons. Over 1 billion photons for every surviving particle of matter. This number, this photon to baryon ratio, is one of the most precisely measured quantities in cosmology, and it tells us something profound about the completeness of the annihilation that occurred in the early universe. Each of those billion photons represents, roughly speaking, a particle-antiparticle pair that was created and then annihilated. For roughly every 1.5 billion particles of matter that were created in the early universe, all but one of them found antiparticle partners and annihilated. Only one survived. One particle out of roughly every billion escaped annihilation. That's the margin. That's the imbalance that made everything possible. The annihilation destroyed 99.999999% of all the matter and antimatter in the universe. The remaining fraction, that tiny, seemingly negligible residue, is the entirety of the physical world. Every galaxy in the observable universe. Every star burning hydrogen into helium. Every planet orbiting those stars. Every ocean of water. Every continent of rock. Every atmosphere of gas. Every molecule of DNA. Every cell in every living organism that has ever existed on Earth or anywhere else in the cosmos. All of it. Every last atom comes from that tiny surplus. 1 part in 1 billion, the leftovers from an almost complete annihilation that converted essentially everything into light. You are made of the residue. The matter that was supposed to be here annihilated with the antimatter and became light. You are made of what was left over. The cosmic microwave background, that faint glow of microwave radiation that permeates every corner of the observable universe, is the graveyard of the other 999,999,999. It's the light produced by the annihilation of almost everything. When you tune a television to a channel with no broadcast and see static, about 1% of that static is caused by cosmic microwave background photons hitting the antenna. You're literally seeing the remnant light of the Great Annihilation, the photons produced when the universe destroyed almost all of the matter and antimatter it had created. That static is the echo of the most thorough act of destruction in the history of reality. The uniformity of the cosmic microwave background tells us something important about how the annihilation happened. The CMB is almost perfectly uniform in every direction. The temperature is the same to within 1 part in 100,000 wherever you look. This means the annihilation happened everywhere in the universe at essentially the same rate and in essentially the same way. There were no special regions where matter survived more than antimatter. There were no pockets where the annihilation was less complete. The process was universal and uniform. Whatever caused the tiny matter excess, it affected the entire universe equally. The tiny fluctuations that do exist in the CMB, those 1 part in 100,000 variations from point to point, are not related to the matter-antimatter asymmetry. They're density fluctuations, slight variations in how much matter was present from one region to another. These fluctuations are the seeds of cosmic structure. Regions that were slightly denser than average attracted more matter through gravity, eventually growing into galaxies and galaxy clusters. Regions that were slightly less dense became the cosmic voids, the enormous empty spaces between the filaments of galaxies that make up the cosmic web. The cosmic microwave background is a snapshot of the universe as it was about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for light to travel freely through space for the first time. Before that moment, the universe was opaque. Photons couldn't travel far before being scattered by free electrons. But when electrons combined with protons to form neutral hydrogen atoms, a process called recombination, the photons were suddenly free to travel unimpeded across the universe. Those photons have been traveling ever since, and they reach our telescopes today as the cosmic microwave background. But the matter-antimatter asymmetry was determined much earlier than recombination. It was determined in the first seconds, possibly the first fractions of a second, after the Big Bang. By the time the universe was a few minutes old, the annihilation was already over. The antimatter was gone. The surviving matter was all that remained. Everything that happened after that point, the formation of atoms, the formation of stars, the formation of galaxies, the evolution of life, all of it was determined by what happened in those first moments. The asymmetry was set. The die was cast. And the rest of the universe's 13.8 billion year history has simply been the unfolding consequence of that initial imbalance. Now here's the question that changes everything. Where did the asymmetry come from? If the laws of physics are symmetric between matter and antimatter, if pair production always creates equal amounts of both, how did the universe end up with slightly more matter than antimatter? What process could have generated an excess of 1 part in a billion? What mechanism could have tipped the scales so slightly, so delicately, that the result was almost nothing, and yet that almost nothing turned out to be everything? The universe should not exist as we know it. The atoms in your body should not exist. The stars should not exist. The galaxies should not exist. According to the laws of physics as we understand them, the great annihilation should have been complete. Matter and antimatter should have destroyed each other totally, leaving nothing but an ocean of light expanding into eternity. And yet, here we are. Something broke the symmetry. And the clues we have, the fragments of evidence that point toward an answer, come from one of the most surprising places in all of physics. They come from the discovery that the mirror between matter and antimatter isn't quite perfect after all. There are cracks in it, tiny, subtle, almost invisible cracks, but they're there, and they might be the reason you exist. This removes the paragraph that names the baryon asymmetry problem and states the standard model can't explain it, since part 4 opens with exactly that. It also trims something tipped the balance. Something allowed 1 particle in every billion to survive. Finding that something, identifying the mechanism that created the tiniest imperfection in the perfect mirror between matter and antimatter, is one of the great quests of modern science. This is the question that haunts physics. It's called the baryon asymmetry problem, and it is one of the deepest unsolved puzzles in fundamental science. Baryons are particles made of 3 quarks. Protons and neutrons are both baryons. They are the building blocks of atomic nuclei, and therefore the building blocks of all ordinary matter. The baryon asymmetry is the observed fact that the universe contains overwhelmingly more baryons than antibaryons, more protons than antiprotons, more neutrons than antineutrons, more matter than antimatter, by a factor that is almost exactly 1 billion and 1 to 1 billion. And the question that has driven decades of theoretical and experimental work is simply this: why? What mechanism in the laws of physics could have produced this asymmetry from an initially symmetric state? What process could have broken the perfect mirror between matter and antimatter and allowed that 1 extra particle in every billion to survive? In 1967, the Russian physicist Andrei Sakharov identified the answer, or at least the framework for the answer. Sakharov was a remarkable figure. He was one of the key scientists behind the Soviet hydrogen bomb program, but later became one of the Soviet Union's most prominent dissidents, campaigning for human rights and nuclear disarmament. He received the Nobel Peace Prize in 1975, but his contribution to physics was equally profound. In a short paper published in 1967, Sakharov laid out 3 conditions that must be satisfied for a matter-antimatter asymmetry to develop in a universe that started out perfectly symmetric. These 3 conditions, now known as the Sakharov conditions, are the theoretical foundation for understanding why matter exists. The first Sakharov condition is that there must exist processes in nature that violate the conservation of baryon number. Baryon number is a quantum number that counts the total number of baryons minus the total number of antibaryons. A proton has baryon number plus 1. An antiproton has baryon number minus 1. In almost every particle interaction ever observed in a laboratory, baryon number is strictly conserved. If you start with a total baryon number of, say, +3, you end with a total baryon number of +3. The number of baryons minus antibaryons never changes. This is one of the most well-established conservation laws in particle physics. But here's the thing. If baryon number is always conserved, then you can never change the total amount of matter relative to antimatter. You can create protons, but only if you simultaneously create antiprotons. You can destroy protons, but only by annihilating them with antiprotons. The net baryon number stays fixed. So if the universe started with 0 net baryon number, equal amounts of matter and antimatter, it would stay at 0 forever. The asymmetry we observe could never develop. For the asymmetry to exist, baryon number conservation must be violated at some level. There must be processes, however rare, that can change the total number of baryons in the universe without making a corresponding change in the number of antibaryons. This might sound like a fatal problem. If baryon number conservation is so well established experimentally, how can it be violated? The answer is subtle and comes from the deep mathematical structure of the Standard Model itself. In 1976, the Dutch physicist Gerard Hooft showed that the Standard Model actually does allow baryon number violation, but only through a very specific and exotic class of quantum processes. These processes are related to the structure of the electroweak force, the unified force that encompasses both electromagnetism and the weak nuclear force. They involve quantum tunneling between different vacuum states of the electroweak field, and they are mediated by objects called instantons at low temperatures and sphalerons at high temperatures. At everyday temperatures and energies, these processes are so fantastically rare that they might as well not exist. The probability of a baryon number violating event happening at room temperature is so astronomically small that you could wait longer than the age of the universe and never see one. The rate is suppressed by a factor of roughly 10 to the negative 164. That's a decimal point followed by 163 zeros and then a 1. For all practical purposes, baryon number is perfectly conserved at low energies. This is why experiments have never observed baryon number violation. The probability is simply too small. But at high temperatures, specifically at temperatures above about 10 to the 15 degrees, which is roughly the temperature of the electroweak phase transition in the early universe, the situation changes dramatically. Sphalerons, which are thermal fluctuations in the electroweak field, become common. They are not suppressed, they happen frequently, and sphalerons violate baryon number. They can convert baryons into leptons and vice versa, changing the baryon number of the universe. In the extreme heat of the early universe, in the first trillionths of a second after the Big Bang, these baryon number violating processes were happening constantly. The first Sakharov condition was satisfied. The second Sakharov condition involves two fundamental symmetries of nature, called C and CP. Understanding these symmetries and how they're violated is crucial, because this is where the mystery becomes most acute and where the experimental evidence is most tantalizing. C symmetry stands for charge conjugation symmetry. It is the statement that the laws of physics should remain unchanged if you replace every particle with its corresponding antiparticle. If C symmetry were exact, then every physical process involving matter would have an exact mirror process involving antimatter occurring at exactly the same rate. Any process that created an excess of matter would be perfectly counterbalanced by a conjugate process creating an identical excess of antimatter. The net result would be zero asymmetry. P symmetry stands for parity symmetry. It is the statement that the laws of physics should remain unchanged if you reflect everything in a mirror, swapping left and right. If you watched a physical process and its mirror image, both should obey the same laws. In 1956, physicists Tsung-Dao Lee and Chen-Ning Yang proposed that parity might be violated in the weak nuclear force. This was confirmed experimentally in 1957 by Qianxiong Wu in a famous experiment involving the beta decay of cobalt-60. Wu showed that the weak force distinguishes between left and right. Electrons emitted in beta decay preferentially emerge in one direction relative to the spin of the decaying nucleus. The weak force violates parity. It treats left and right differently. This was shocking at the time. It overturned a deeply held assumption in physics. Now, after parity violation was discovered, physicists hoped that the combined symmetry CP would still hold. CP symmetry means that if you simultaneously replace all particles with their antiparticles and reflect everything in a mirror, the laws of physics should remain unchanged. Even though C is violated and P is violated individually, perhaps the combination CP is preserved. If you flip the charges and flip the mirror at the same time, maybe everything balances out. But in 1964, James Cronin and Val Fitch demonstrated that this hope was wrong. Working at Brookhaven National Laboratory, they studied the decay of neutral kaons, particles containing a strange quark and a down antiquark, or vice versa. Neutral kaons come in two varieties that physicists call K-long and K-short, based on their lifetimes. K-short decays quickly into 2 pions. K-long lives longer and decays into 3 pions. If CP symmetry were exact, K-long could never decay into 2 pions, but Cronin and Fitch found that a tiny fraction of K-long decays, about 2 in every 1,000, did produce 2 pions. This was direct evidence of CP violation. The combined symmetry of charge conjugation and parity was broken. The laws of physics, at some deep level, do distinguish between matter and antimatter, even when you account for the mirror flip. This discovery was so unexpected and so important that Cronin and Fitch received the Nobel Prize in Physics in 1980 for it. CP violation meant that the laws of physics are not perfectly symmetric between matter and antimatter. There is a slight preference, a tiny bias, built into the fundamental equations. Certain processes involving matter happen at slightly different rates than the corresponding processes involving antimatter. The mirror between the two isn't quite perfect. It has a crack. Since the discovery of CP violation in kaons, physicists have found it in other particle systems as well. In the early 2000s, 2 particle physics facilities were built specifically to study CP violation in detail. The Babar experiment at the Stanford Linear Accelerator Center in California and the Bell experiment at the KEK Accelerator Complex in Tsukuba, Japan. Both facilities were designed to produce enormous numbers of B mesons, particles containing a bottom quark. These experiments confirmed that CP violation also occurs in B meson decays, and they measured it with high precision. The pattern of CP violation they found was consistent with the theoretical framework developed in 1973 by Makoto Kobayashi and Toshihide Masukawa. Kobayashi and Masukawa had proposed that CP violation could arise naturally in the standard model if there were at least 3 generations of quarks. At the time of their proposal, only 2 generations were known. The up and down quarks of the first generation, and the charm and strange quarks of the second generation. Kobayashi and Masukawa predicted that a 3rd generation must exist, containing what we now call the top and bottom quarks. The bottom quark was discovered in 1977. The top quark was discovered in 1995. Both discoveries confirmed the Kobayashi-Masukawa prediction, and the CP violation observed in the B meson experiments matched their theoretical framework with remarkable precision. Kobayashi and Masukawa received the Nobel Prize in Physics in 2008 for their work. The third Sakharov condition is that the baryon number violating and CP violating processes must occur out of thermal equilibrium. This condition is necessary for a subtle but important reason. In a system that is in thermal equilibrium, meaning everything is at the same temperature and reactions proceed in both directions at equal rates, every process is exactly balanced by its reverse process. Particles are created at the same rate they're destroyed. Any asymmetry generated by one reaction is immediately erased by the reverse reaction. The system is in a state of perfect dynamic balance, and no net asymmetry can develop or persist. For an asymmetry to be generated and preserved, the system must be driven out of equilibrium. Something must happen that prevents the reverse reactions from erasing what the forward reactions create. In the context of the early universe, departures from thermal equilibrium can occur during phase transitions, moments when the fundamental properties of the universe change as it cools. These phase transitions are analogous to water freezing into ice. As water cools below 0 degrees Celsius, it undergoes a phase transition. The molecules rearrange themselves into a crystalline structure. During this transition, the system is out of equilibrium. The water is changing from one state to another, and the forward process, freezing, is not balanced by the reverse process, melting. Something similar may have happened in the early universe. As the universe cooled through certain critical temperatures, the properties of the fundamental forces changed. The electroweak phase transition, which occurred when the universe was about 1/1,000,000,000th of a second old, was a moment when the electromagnetic force and the weak nuclear force separated from each other. Before this transition, they were unified as a single electroweak force. After the transition, they became distinct forces with different properties. If this phase transition was sufficiently violent, proceeding through the formation and expansion of bubbles of the new phase within the old phase, much like bubbles of steam forming in boiling water, then it could have driven the universe far enough from equilibrium for the asymmetry to be generated and frozen in before the reverse processes could erase it. So all three Sakharov conditions can, in principle, be satisfied. Baryon number violation exists in the standard model through Sphaleron processes. CP violation has been experimentally observed in kaon and B-meson decays, and the expanding, cooling universe provides natural departures from thermal equilibrium through phase transitions. The framework is in place. The ingredients exist. So here is the obvious question. Can the standard model, with its known particles and forces and its observed CP violation, produce the matter-antimatter asymmetry we see in the universe? The answer is no. And this is one of the most significant and frustrating results in modern physics. All three Sakharov conditions are met within the standard model, but the amounts are wrong. The CP violation we've measured in kaon and B-meson experiments is real and confirmed, but it is quantitatively far too small to produce the observed baryon asymmetry. When physicists perform the calculation, plugging in the known values of CP violation and the known rates of Sphaleron processes and the known properties of the electroweak phase transition, the resulting asymmetry falls short of what's needed by many orders of magnitude. The standard model predicts an asymmetry that is roughly 1 billion times smaller than the 1 billion to 1 ratio we observe. 1 billion times too small. The gap between prediction and observation is enormous. There's also a problem with the third condition. For the electroweak phase transition to drive the universe far enough from equilibrium, the transition needs to be what physicists call strongly first order, meaning it proceeds through bubble nucleation in a sudden, violent manner. But within the standard model, given the measured mass of the Higgs boson at about 125 billion electron volts, the electroweak phase transition is not first order. It's a smooth crossover, a gradual change rather than a sudden one. This means the departure from equilibrium is not sharp enough to preserve whatever tiny asymmetry the standard model's CP violation might generate. The conclusion is inescapable. The standard model cannot explain the matter-antimatter asymmetry of the universe. There must be new physics beyond the standard model. There must be new particles, new forces, new interactions, or new sources of CP violation that we haven't yet discovered. Whatever created the 1 part in a billion excess of matter over antimatter involved physics that our current theories don't fully describe. The matter-antimatter asymmetry is direct, unambiguous evidence that the standard model is incomplete. It's a signpost pointing toward undiscovered physics. Several theoretical frameworks have been proposed to explain the asymmetry, and each makes different predictions that can potentially be tested by experiments. One prominent class of theories involves leptogenesis. In these models, the asymmetry is generated not in the baryon sector directly, but in the lepton sector, among particles like neutrinos. Very heavy right-handed neutrinos, particles predicted by many extensions of the standard model but never yet observed, could decay in a CP-violating way that produces more leptons than antileptons. This lepton asymmetry would then be partially converted into a baryon asymmetry through sphaleron processes, which can interchange baryon number and lepton number. Leptogenesis is elegant and theoretically well motivated, particularly because we already know that neutrinos have properties that the simplest version of the standard model doesn't predict. Specifically, that they have tiny but non-zero masses. The mechanism that gives neutrinos their masses could naturally involve the heavy right-handed neutrinos that leptogenesis requires. The challenge is that these heavy neutrinos might have masses far too high to produce directly in any particle accelerator we could realistically build. Another class of theories proposes that the asymmetry was generated during the electroweak phase transition itself, a scenario called electroweak baryogenesis. For this to work, new physics must make the electroweak phase transition strongly first order and must provide additional sources of CP violation beyond what the standard model contains. Extensions of the standard model that include additional Higgs bosons, supersymmetric particles, or other new scalar fields could potentially achieve both goals. The appeal of electroweak baryogenesis is that the energy scales involved are relatively low by particle physics standards, meaning the new particles and interactions it predicts might be detectable at the Large Hadron Collider or at future colliders currently being planned. Current experiments around the world are searching for clues. The LHCb experiment at CERN studies CP violation in the decays of particles containing charm and bottom quarks with unprecedented precision, looking for deviations from standard model predictions that might reveal new sources of CP violation. Neutrino experiments like T2K in Japan, NOVA in the United States, and the upcoming deep underground neutrino experiment known as DUNE, which is being built in South Dakota, are searching for CP violation in the oscillations of neutrinos as they travel long distances. If neutrinos and antineutrinos oscillate between flavors at different rates, that would be a completely new source of CP violation not present in the quark sector. Early results from T2K have shown hints of such an effect, but the data are not yet conclusive. DUNE, expected to begin full operations in the coming years, will measure this with far greater precision and could provide definitive evidence. Other experiments take different approaches entirely. Electric dipole moment searches look for an asymmetric distribution of electric charge within fundamental particles, like the electron or the neutron. If a particle has a permanent electric dipole moment, meaning its charge is distributed slightly unevenly, that would be a signal of CP violation beyond what the standard model predicts. Current experiments have placed extraordinarily tight limits on the electron's electric dipole moment, constraining many theoretical models. Future experiments with improved sensitivity could either detect a signal or rule out large classes of theories. The search also continues at the highest energies. The Large Hadron Collider has not yet found any new particles beyond those predicted by the standard model. This absence of discovery, while disappointing to many physicists, is itself informative. It tells us that whatever new physics is responsible for the matter-antimatter asymmetry might exist at energy scales higher than the LHC can reach. Proposed future colliders, including the Future Circular Collider at CERN, which would be roughly 7 times more powerful than the current LHC, and proposed muon colliders, which could reach even higher energies in a more compact facility, might be needed to directly discover the new particles or interactions responsible for the asymmetry. At CERN, the alpha and base experiments continue to make increasingly precise measurements of the properties of antihydrogen and antiprotons, comparing them to their matter counterparts with extraordinary accuracy. Any difference, however small, between the properties of matter and antimatter particles would be a revolutionary discovery, potentially pointing toward the mechanism that generated the cosmic asymmetry. So far, every measurement has shown perfect agreement between matter and antimatter, consistent with what we expect. But the precision of these measurements improves every year, and the next decimal place might reveal a difference. Let me bring this back to what it means for you. The atoms in your body exist because, in the first fraction of a second of the universe's existence, the laws of physics treated matter and antimatter with an almost imperceptible bias. A bias so slight that for every billion particle-antiparticle pairs that were created and destroyed, one extra matter particle was left over. 1 in a billion. That's the surplus. That's the margin. That's the difference between a universe of pure light and a universe of stars and planets and people. Everything you see when you look up at the night sky, every galaxy, every nebula, every star, is made from that surplus. Every atom on Earth is part of that tiny residue. The iron in your blood, the calcium in your bones, the carbon in your DNA, the oxygen you're breathing right now, all of it was once part of that 1 in a billion excess that escaped the Great Annihilation 13.8 billion years ago. The universe came breathtakingly close to not producing any material structures at all. It came within 1/billionth of being a void of pure radiation. A cosmos with no atoms, no chemistry, no complexity, no life, just photons expanding and cooling forever. The margin between existence and non-existence was almost zero. And the mechanism that made the difference, the tiny crack in the mirror between matter and antimatter, is something so subtle that we've spent more than half a century searching for it and still haven't found the complete answer. We've found pieces. We know CP violation exists. We know it occurs in kaon decays and B-meson decays. We know the standard model contains mechanisms for baryon number violation. But the pieces don't add up. The known CP violation is too small. The known phase transition is too smooth. Something else is needed. Something we haven't discovered yet. And that's where things stand today. We know the asymmetry is real because we're here. We know approximately how large it was, about 1 part in a billion, because we can measure the photon to baryon ratio in the cosmic microwave background. We know the theoretical framework for generating such an asymmetry, the 3 Sakharov conditions. We know that the standard model satisfies all 3 conditions, but not strongly enough to explain what we observe. We know that new physics beyond the standard model must be responsible. And we are actively searching for that new physics in laboratories and observatories around the world, probing the deepest structure of matter and energy, looking for the hidden asymmetry that made existence possible. The story of antimatter is ultimately a story about imperfection. The universe is not here because of some grand design or because the laws of physics are perfectly tuned for our benefit. It's here because of a flaw, a crack in the symmetry, a tiny deviation from perfection that allowed 1 particle in every billion to escape annihilation. We exist because the mirror between matter and antimatter is not quite perfect. If it were perfect, if the symmetry were exact, there would be nothing, no matter, no structure, no life, only light. The imperfection saved us. The flaw created us. Every atom in your body is a testament to that imperfection. Every star in the sky is evidence of a broken symmetry. The entire visible universe, all 2 trillion galaxies, all the hundreds of billions of stars in each galaxy, all the planets and moons and asteroids and comets, all the gas clouds and dust lanes and cosmic filaments, every last bit of it exists because the laws of physics are not quite symmetric between matter and antimatter. Because somewhere, embedded in the deepest structure of reality, there is an asymmetry so small it's almost undetectable. And that asymmetry made everything. We don't yet know the full nature of that asymmetry. We've found fragments of it in particle accelerators. We've measured hints of it in the behavior of kaons and B mesons. We may soon find more of it in the oscillations of neutrinos, but the complete picture remains hidden. The full mechanism that broke the mirror and allowed matter to survive is still one of nature's deepest secrets. Experiments are running right now, at this very moment, in underground laboratories and particle accelerators and satellite observatories, searching for the answer. The next generation of physicists may find it, or it may take generations more. We don't know how far we are from the answer, but we know the question matters. Because the answer to why matter survived and antimatter vanished is, in the most literal and precise sense imaginable, the answer to why anything exists at all. Why there are atoms rather than just light. Why there are stars rather than just radiation. Why there is a universe capable of producing life, consciousness, curiosity, and wonder, rather than a vast empty sea of photons cooling slowly toward absolute zero in the darkness forever. You are the evidence. Your existence is the proof that the symmetry was broken. Every breath you take, every thought you form, every heartbeat, every moment of your life is made possible by an imperfection in the laws of physics so small that it took humanity decades of effort with the most sophisticated instruments ever built to detect it at all. You are one part in a billion, the residue, the survivor, the matter that antimatter didn't destroy. And the reason you survived is written into the deepest structure of reality itself, in a language we're still learning to read.